Hi there, Gordon West, WB6NOA with Radio School, and congratulations, this is the last module, tape number 6 on audio cassette, in preparation for your upcoming 2002 plus extra class license. Now, we're going to be covering antennas on this portion of the audio cassette, plus the big review that you want to play several times just before you take your extra class test. Now, to find out where a test location is near you, and to find out what to bring and where exactly it's located, call the following phone number, 1-800-669-9594. One more time, to locate an extra class examination near you, call 1-800-669-9594, and they'll give you a nice list of, right on the phone, examination times and places. So call that number, 1-800-669-9594. Tell them you've been studying on audio and you want to take the course test, and that Gordo recommended this phone number to take the exam, and they'll get you anywhere in the country lined up with a test giver. And at the conclusion of this audio course, we'll tell you exactly what to bring, such as a copy of your general or your grandfathered advanced class license. Be thinking about you need a copy of your present license. All right, let's start with E9A01, all about antennas. You'll have 5 test questions on antennas. 5 groups. Our first group is on the isotropic radiator. Which of the following describes an isotropic radiator? Well, that's a theoretical radiator used to compare other antennas. Keyword theoretical, it's not real. Now, why do we refer to an isotropic radiator? Well, we do so when comparing the gains of directional antennas. And how much gain does, let's take a half-wave dipole have, which is sometimes what we compare antennas to. The half-wave dipole over the isotropic radiator has about 2.1 dB gain. So when you're ready to go out there and buy that new super directional beam Yagi antenna, and it has 9 dB of forward gain compared to an isotropic radiator, it really has only about 7 dB of gain compared to a half-wave dipole. Which of the following antenna has no gain in any direction? Well, the type of antennas with no gain in any direction is called the isotropic radiator. Which of the following describes the radiation pattern of an isotropic radiator? That would be a sphere with the antenna in the center, like half a tennis ball. Why would one need to know the feed point impedance of an antenna? Oh, that's important. You want to match the impedance for maximum power transfer, usually 50 ohms. What factors determine the radiation resistance of an antenna? Well, the radiation resistance is affected by antenna location with respect to nearby, usually metal objects, and the antenna conductor length and diameter ratio. What is the term for the ratio of the radiation resistance of an antenna to the total resistance of the system? We call that antenna efficiency. And what is included in the total resistance of an antenna system? It's radiation resistance plus the ohmic, OHMIC, resistance. The folded dipole, that's a nice antenna. That's a dipole whose ends are connected by 1/2 wavelength piece of wire. And antenna gain that we talked about a few moments ago, that's a numerical ratio relating the radiated signal strength of an antenna to that of another antenna, usually a dipole or the isotropic radiator. What is meant by antenna bandwidth? Bandwidth. That's the frequency range over which an antenna can be expected to perform well. And how can the approximate beam width of an antenna be determined? Now, bandwidth and beam width are different. Beam width are the 2 points where the signal strength of the antenna is down 3 decibels, or half, from the maximum signal point. and we compute the angular difference for beam width. How about antenna efficiency? How do we calculate it? Radiation resistance divided by total resistance times 100. Now, how can we make a HF grounded vertical antenna, how can we make it more efficient compared to that of a half-wave dipole? Well, the key to a good HF grounded vertical antenna is a good ground radial system. And the antennas generally are quarter wavelength long if they're HF vertical, so you need a radial system that is also at least a quarter wavelength long. And you need multiple radials. The more radials you add, the lower the angle of radiation and the further you're going to be able to communicate. And again, what's that theoretical reference antenna called? The isotropic radiator. Now, let's take some antennas and look at their gain when compared to the isotropic radiator. And the reason these are important questions, the QPC did a great job of adding these in, is because many times antenna manufacturers that are just getting started will reference their directional antennas to the isotropic radiator, and it looks like they have 2 more dB gain than they really do. How much gain does an antenna have over a half-wave dipole when it is 6 dB gain over an isotropic radiator? This antenna, 6 dB gain, but they don't say to what. Usually they mean the isotropic radiator. Well, 6 dB gain minus 2.154, 3.9 dB. So 3.9 dB for the 6 dB gain advertised antenna. How about a 12 dB gain antenna over an isotropic radiator to a half-wave dipole? 12 minus 2.1 is 9.9. Not as much gain when compared to a real half-wave dipole. Which of the following describes the directivity of an isotropic radiator? Well, it has no directivity at all. Like half a tennis ball, it radiates and goes out in all directions. What is meant by the radiation resistance of an antenna? That's the equivalent resistance that would dissipate the same amount of power as that radiated from an antenna. Polarization, remember it's the electric lines of force, the E field. What determines the free space polarization of an antenna? The orientation of the electric field, the E field. Now in free space, H field radiation pattern shown in the figure E9-1, what is the 3 dB beam width? Now, we need to look carefully at figure E9-1 and notice that the main lobe of the pattern intersects the 3 dB points at approximately minus 25 degrees. Minus 25 degrees to the left of the antenna, minus 25 to the right. The beam width would then be a total of 50 degrees. Now, let's take a look at this radiation pattern nice and tight here. Yeah, okay, I've got it. In the free space H field pattern shown in E9-1, what's the front to back ratio? Well, let's take a look and see where that rear lobe is. And the rear lobe shows about minus 18 dB down from the front lobe. And we calculate that minus 18 by looking at the vertical axes of this chart. We see minus 24, minus 12, minus 6. It's in from minus 12, but it's not as great as minus 24. So minus 18 is close enough. The other answers, 36, 24, 14. Nope, not even close. Minus 18. Just think that when you're 18, you'll be able to have your own antenna, kids. In the free space H field pattern shown in this figure, what is the front to side ratios? Well, the sides have a little minor lobe going out, and they are about 14 dB down. So 14 dB. What information is needed to accurately evaluate the gain of an antenna? Well, to calculate the gain of an antenna, we need to know the radiation resistance. We need to know the patterns, E field and H field. We need to know the loss of the elements of the coil, loss resistance. So all of these are choices in evaluating the gain of an antenna, which is not an important reason to evaluate a gain antenna across the whole frequency band for which it's designed. Well, one thing that will not be true in this question is the dielectric constant may vary significantly. The varying dielectric constant of an antenna is not an important reason to evaluate the gain. We would evaluate the gain to see if it falls off rapidly or just a little bit on the whole frequency band. We'd evaluate the gain to see what the feed point impedance is that may change radically with frequency. And we would evaluate the rearward pattern lobes, the rear lobes, that may excessively change with frequency. But something that's not important is a dielectric constant that may vary significantly. What usually occurs if a Yagi antenna is designed solely for maximum forward gain? Well, if it's just for maximum forward gain, the feed point impedance is usually relatively low, too low for a direct coax connection. If the boom of a Yagi is lengthened and the elements are properly retuned, what almost always occurs, gain increases, which means the longer the boom, the more gain. No one can come up with more gain with a shorter boom, no matter how many elements have been added to that boom. Boom length, all critical important in determining gain. You can just look at an antenna saying, that antenna has gain because it's on an 80-foot boom. What type of computer program is commonly used for modeling antennas? We call that method of moments. What is the principle of method of moments analysis? Well, that is a wire is modeled as a series of segments, each having a distinct value of current. And using this, we can determine the approximate gain of an antenna that we're computer modeling. Now, sometimes hams will phase vertical antennas. If you have a lot of property and you don't want to put up a big beam, you want to stay with verticals, you can phase them to develop directionality. And they have one question out of the next series of, let's see, they've got 5 questions. So one out of the 5 will possibly be on your exam. Question E9C01. You've got 2 quarter-wave vertical antennas spaced a half wave apart and fed 180 degrees out of phase. What is going to be the radiation pattern? All right, that is, again, think about this, 2 quarter-wave verticals, half wave apart, 180 out of phase by your coax feed lines. It'll be a figure 8 end fire in line with the antennas. Now, if you have 2 quarter-wave verticals spaced a quarter wave apart and fed 90 degrees out of phase rather than 180, it will be a unidirectional cardioid radiation pattern. If you had 2 quarter-wave verticals spaced a half wave apart and fed in phase, now we're back to figure 8, but this will be figure 8 broadside to the antennas. So remember, quarter-wave antennas, half wave apart, will be figure 8, but half wave out of phase will be end of fire in line with the antennas, and if they are in phase rather than out of phase, they will be figure 8 broadside to the antenna. What's the radiation pattern of these 2 quarter-wave vertical antennas spaced a quarter wavelength apart and fed 180 degrees out of phase? 180. Now watch this, a quarter wave apart. First they were a half wave, figure 8 end fire. Now they're a quarter wave, they are still figure 8 end fire in line with the antennas. How about these 2 quarter wave vertical antennas spaced an eighth of a wavelength apart and fed 180 degrees out of phase? They will still be figure 8 end fire in line with the antennas. But the pattern won't be nearly as defined as if they were spaced a quarter wave or even a half wave apart. What is the radiation pattern for these 2 quarter wavelength vertical antennas spaced a quarter wavelength apart, fed in phase? Well, in phase, they will develop an elliptical pattern. All right, review these 6. Hopefully one may not be on your test because you almost have to look at charts to figure these out. But just so you know that here are the answer to those 6. Now let's go to the resonant rhombic antenna, and rhombics are major. Which of the following is the best description of that rhombic antenna? Well, the resonant rhombic is bidirectional. It's 4-sided, each side approximately 1 wavelength long, open at the end opposite of the transmission line. That is a resonant rhombic antenna. What are the advantages of a terminated rhombic antenna? Well, that is wide frequency range, high gain, and high front to back ratio. Disadvantages of the terminated rhombic antenna would be a large area and the huge 4 sturdy supports to keep it up for proper installation. It's major. And what is the effect of a terminating resistor on that rhombic antenna? The terminating resistor changes the radiation pattern from essentially bidirectional to essentially unidirectional. What type of antenna pattern over real ground is shown in the figure E9-2? Well, this figure shows over real ground the elevation pattern of the main lobes of the antenna. And if we look at this antenna, this is not bad, although it tells me it's pretty close to Earth. The H-field antenna pattern, the elevation angle of the peak response, that is the strongest response, is, let's see, it looks like 7 degrees. Yep, 7 degrees. The front to back ratio, wow, that's good. That's way down at, let's see, just under 30. It's 28 minus 28 dB. But in this case, we just say a positive 28 dB. And if we look at this figure, how many elevation lobes appear in the forward direction? 3 big ones and 1 small one for a total of 4. How is the far field evaluation pattern of a vertically polarized antenna affected by being mounted over seawater? Ah, mariners, you'll love this. Seawater versus rocky ground. Well, the low angle radiation increases. This means the ultimate skip distance will be lengthened. If only a modest on-ground radio system can be used with an 1/8 wavelength high inductively loaded vertical antenna, what would be the best compromise to minimize near field losses? In other words, if you buy one of those manufactured multi-band antennas, how can you improve its performance? Well, for the ground plane, a wire mesh screen at the antenna base and put that in 1/8 wavelength squares, you'll have a great ground system. Wire mesh screen at the antenna base and 1/8 wavelength square. Now, one characteristic of an antenna called beverage. Beverage is, for best performance, it needs to be long. In fact, longer than 1 wavelength. Electric field. For the Yagi antenna with 3 elements mounted parallel to the ground, they're asking the electric field. That 3-element Yagi parallel to the ground would be horizontally polarized. And what strongly affects the shape of the far field low angle elevation pattern of a vertically polarized antenna? Well, certainly the conductivity and dielectric constant of the soil. Conductivity of the soil. Where are elevated radial counterpoises popular with vertically polarized antennas? Well, they're most popular when you want to reduce the near-field ground losses compared to on-the-ground radial systems using more radials. The elevated radial counterpoise reduces the near-field ground losses. And back to that rhombic, the terminated rhombic, a unidirectional antenna terminated in a resistance equal to its characteristic impedance. Now let's take a look at E9D01, all about going into space. What factors determine the receiving antenna gain required at an amateur satellite station down here on Earth? Well, height of the antenna, transmitter power, and antennas of satellites. In other words, what kind of antennas do the satellites have, giving us a so-so signal back here or a strong signal back here? What factors determine the EIRP required by an amateur satellite station in Earth operation? Effective isotropic radiated power. Again, satellite antennas and height, satellite receiver sensitivity. If you know these factors, satellite antennas and height, satellite receiver sensitivity, you'll be able to calculate the EIRP that you're going to need to be able to work that satellite. Now, sometimes hams will go to dish antennas, especially up at 10 gigahertz to work the new phase 3D satellite. What is the approximate beam width of a symmetrical pattern antenna with a gain of 20 dB compared to the isotropic radiator? 20 dB is 20 degrees. Now, just remember that. Trust me, 20 dB, 20 degrees. Because as we have more dB, the degrees will go down. It'll be a tighter pattern. As we have less dB, the degrees will go up. Beam width in degrees is equal to a fixed value of 203 divided by the square root of 10 raised to the power represented by the antenna gain in dB divided by 10. Oh, you just want to remember 20 is 20, all right? If I said, how does the gain of a parabolic dish antenna change when the operating frequency is doubled? When you double the frequency, gain of that same dish increases by 6 dB, or 4 times. How is circular polarization produced using linearly polarized antennas? And by the way, whenever you're writing your magazine articles about antennas, the plural of antennas is antennas, not antennae. Antennae are those little feelers found on bugs. Antennas. Well, the way we come up with circular polarization using linearly polarized antennas, we arrange two Yagis perpendicular to each other, one vertical, one horizontal, with the driven elements in the same plane fed 90 degrees out of phase. How does the beam width of an antenna vary as the gain is increased? Well, here we go. 20 is 20. Beam width will decrease. In other words, it gets tighter, which we want, as the gain is increased. Now, why does a satellite communications antenna system for Earth operation need to have rotators for both azimuth and elevation? Well, that's easy. In order to track the satellite as it orbits the Earth. Now, for a shortened vertical antenna, where should a loading coil be placed to minimize losses and produce the most effective performance? Well, for mobile antennas, we recommend putting the big, huge loading coil near the center in that vertical radiator. That is called center loading. It produces a most effective power. And center loading with a capacity top hat even does better. Why should an HF mobile antenna loading coil have a high ratio of reactance to resistance? Well, you want minimum resistance, and you want that high reactance to minimize losses. It'll cause the Q to become quite high, which is what you want, a high Q antenna. Disadvantage of that trap antenna you can buy? Not many. They're pretty good for home use, but the trap antenna will radiate harmonics if you hook it up to an old radio without a lot of harmonic filters. How must the driven element of a 3-element Yagi be tuned? Using a hairpin matching system. Well, the driven element reactance is capacitive. So remember, with a hairpin matching system, it is the reactance capacitive. What is the equivalent lump sum constant network for a hairpin matching system of a 3-element Yagi? Well, the equivalent lumped constant network for the hairpin matching system is called an L network. So hairpin, think of it in the L network. And what happens to the bandwidth of an antenna as it's shortened through the use of loading coils? Well, the bandwidth will be decreased. When you shorten a vertical antenna with loading coils, bandwidth gets tighter and losses increase. What's the advantage of using top loading in a shortened HF vertical antenna? It improves radiation efficiency. Top loading, that capacity hat, something good for your mobile antenna. And do you know the approximate input terminal impedance at the center of a folded dipole? Folded dipole is, that's right, 300 ohms. And why do we use a loading coil with an HF mobile antenna? Well, we need to tune out the capacitive reactance. And the advantage of using the trap antenna uses for multi-band operation. Trap antenna, multi-band, as well as harmonics. And what happens at the base feed point of a fixed length HF mobile antenna as the frequency of operation is lowered? Well, the feed point of a fixed length HF antenna, the resistance decreases and the capacitive reactance increases as you go lower in frequency. Now let's get back to that beam width. Remember, 20 degrees, 20 dB. If I said we had 30 dB, it would come out a nice tight 6.4 degrees. The beam width of a symmetrical pattern antenna, like a dish antenna with a gain of 30 dB, as compared to an isotropic radiator would be 6.4 degrees. What is the beam width of a symmetrical pattern antenna with a gain of 20? 20 is 20. All right? 20 degrees, 20 dB. 15 dB is now out to a wide 36 degrees. And if we went to 12 dB, 12 dB would be 51 degrees. Now again, to calculate that, remember that beam width formula? It's in my book, page 226. Beam width, now remember that, beam width in degrees is equal to a fixed value of 203 divided by the square root of 10 raised to a power represented by the antenna gain in dB divided by 10. So I think you best just memorize the numbers. And again, let's go over those numbers one more time for the dish antenna. 20 dB, 20 degrees. 15 dB, 36 degrees. 12 dB, 51 degrees. See it blossoming out? And if we go the other way and add gain of 30 dB as compared to 20, 20 going to 30, 20 is 20, 30 is way down at 6.4 degrees. All right, 20 is 20, 30, nice and tight, 6.4, 20 is 20, 15 dB is 36 degrees, and 12 dB is way out at 51 degrees. What system matches a high impedance transmission line to a lower impedance antenna by connecting the line to the driven element in two places spaced a fraction of a wavelength each side of the center? That's called the delta matching system, much like the letter D. What system matches an unbalanced feed line to an antenna, unbalanced meaning coax, to an antenna by feeding the driven elements both at the center of the element at a fraction of a wavelength to one side of center? That's called the gamma matching system. What impedance matching system uses a short perpendicular section of transmission line connected to the feed line near the antenna? We call that the stub matching system. Now, if we're working on the approximate capacitance of the resonating capacitor in a gamma match antenna for a Yagi for the 20 meter band, the gamma match is normally around 140 picofarad. This is just one of these numbers you need to know, 140 picofarad. On the 10 meter band, it's down to 70 picofarad. So 10 meters, the gamma matching capacitance to cause that capacitor to resonate is 70 picofarad, and on 20 meters it's 140 picofarad. Velocity factor of transmission line, that's the velocity of the radio waves on the transmission line divided by the velocity of light in a vacuum. And the big variance of velocity factor, what determines it is dielectrics in the line. In other words, what is that material separating the center conductor from the outside braid? Why is the physical length of coax cable transmission line shorter than its electrical length? Well, that's because RF energy moves slower, shorter, slower along the coaxial cable. Typical velocity factor of coax, polyethylene dielectric, 0.66. That's right. What would be the physical size of a typical coaxial transmission line that is electrically 1/4 wavelength long at 14.1 megahertz? Now, for this problem, we need to work the numbers 984 times 0.25. That's because the coax is 1/4 wavelength long. Then multiply the result by 0.66, the velocity factor. Remember, 0.66, the velocity factor for most common coax. Now, we're assuming that this value, 0.66, for these problems. Divide the total by 14.1. That's the frequency in megahertz. And the length comes out about 11.51 feet. Yikes, they want the answer in meters. So divide 11.5 by, let's make it 3 feet to the meter. And the results will be 3.83, but 3.5 meters in answer C is the closest. Now, another way to do this, to calculate coax in meters, would be substitute 300 for the 984. This will eliminate one step in the conversion. What is the physical length of a parallel conductor feed line that is electrically 1/2 wavelength long at 14.1? Well, in this problem, the parallel conductor feed line, 1/2 wavelength long at 14.1, should have a velocity factor of about 0.95. And yep, now they include that in the question, 0.95. All right, 984 times 0.5 times 0.95 and divide by 14.10, the frequency in megahertz, convert to meters, and you end up with about 10 meters. Now wait a minute, there's a much easier way of doing this. They want to know physical length of a piece of coax cable for 14.1 megs. Well, that's the 20-meter band. So what's 1/4? Because they want a 1/4 wavelength long section of 20 meters. That's 5 meters. And because of the velocity factor, it's going to be a little bit less than that. So 3.5 meters is your closest answer. Their other answers are miles away. Now, for the half wavelength at 14.1, what's a half a wave of 20 meters? 10 meters. And that is the correct answer because there's almost no velocity factor in this at all. They're using feed line that is parallel conductor. What parameter best describes the interactions at the load end of a mismatched transmission line? Well, we'll have reflection. Just like SWR, standing wave ratio, those are reflections. It's called the reflection coefficient. Which of the following measurements describes a mismatched transmission line? How about 1-to-1 SWR? No, that's actually good. An SWR greater than 1:1 would describe a mismatched transmission line. SWR, keywords SWR, greater than 1:1. Now let's go back to 450 ohm ladder line at 50 megs. What band is that? That is the 6-meter band, as compared to 0.195 inch diameter coax cable, which is that little tiny junk RG58 that we would never use at 50 megs. They say, what characteristic will the ladder line have at 50 megs as compared to little teeny coax? It'll have lower loss in dB per 100 feet, the ladder line. Certainly will. May require some matching up at the beam, but nonetheless, ladder line will have much lower loss. What is the term for the ratio of the actual velocity at which a signal travels through a transmission line when compared to the speed of light in a vacuum? We call that in coax the velocity factor. And let's try another one. Physical length of the typical coax, that is velocity factor 0.66, a quarter wave long at 7.2 megahertz. How many meters is the 7 megahertz band? That's 40 meters. And what is 1/4 of 40 meters? Just think about it. 1/4 of 40 meters, that's 10 meters of coax length. But remember, we have a velocity factor of a whopping 0.66, so we're going to reduce that 10 meters of coax down to 6.9 meters of coax, and that is the correct answer. Incorrect answer would be 24, 50 meters, and 10 meters. Nope. So take the band in megahertz, think in your head how many meters that band is, then 1/4 of it, and then if it's for coax cable, a little bit less than that. What kind of impedance does a 1/8 wavelength transmission line present to a generator when the line is shorted at the far end? All right, 1/8 wave shorted is inductive reactance. That's the kind of impedance it has. 1/8 shorted, inductive reactance. 1/8 wave open is capacitive reactance. Quarter wave open, very low impedance. Quarter wave shorted, very high impedance. Now, before we claim victory, making it all the way to the top and completely through the extra, let's quickly review some of those important antenna points. What's that antenna? That's a theoretical radiator. It's called a isotropic, and has about 2.1 dB gain, less than a half-wave dipole. So the half-wave dipole over an isotropic has 2.1 gain. And the isotropic is a sphere with the antenna in the center. Do you remember what kind of an antenna is connected when the ends are connected by a 1/2 wavelength piece of wire? It's called a folded dipole antenna. And the numerical ratio relating to radiated signal strength of an antenna to that of another antenna is antenna gain, bandwidth, frequency range over which an antenna works, beam width, though 2 points where the signal strength of the antenna is down 3 dB. Antenna efficiency, radiation resistance divided by total resistance times 100. And install what beneath a vertical antenna to improve its performance? A good ground system. Antenna radiation resistance, that's the equivalent resistance that would dissipate the same amount of power as radiating from an antenna. And remember, orientation is the E field. If it is vertically polarized, the E field is vertical. Horizontally, the E field is horizontal. Be sure and note that figure E9-1, that they'll probably give you one test on the exam knowing the radiation characteristics of the antenna. And what do they call that principle where a wire is molded as a series of segments, each having a distinct value? It's called methods of moments. And if you make a Yagi antenna longer by making the boom longer, gain will always increase. And don't forget the radiation pattern, 2 quarter wave verticals spaced half wave apart, fed 180 degrees out of phase, 180 out of phase, half wave apart, quarter wave verticals, figure 8 end fire in line with the antennas. Quarter wave 180 degrees out of phase, a quarter wavelength apart, still figure 8 in fire. Quarter wave 180 degrees out of phase, eighth wave still figure 8 end fire. Now, a quarter wave vertical antenna spaced a quarter wave apart fed 90 degrees out of phase will be unidirectional. And the radiation pattern for two quarter wave vertical antennas 1/8 apart, 180 degrees. Remember, that's figure 8 in fire in line with the antennas. Radiation pattern of two quarter wave verticals spaced a quarter wavelength apart and fed in phase. In phase will be elliptical. In phase, elliptical. And what kind of an antenna is bidirectional, four-sided, each side approximately one wavelength long, open at the end, opposite a transmission line, open? That is a resonant rhombic antenna. Remember, resonant has the letter O in it. Resonant is open. The terminated rhombic antenna has wide frequency range, high gain, and a high front to back ratio. The problem with the terminated rhombic antenna is it requires a large area and four sturdy supports for proper installation, and the effect of a terminating resistor on a rhombic antenna is it changes the radiation pattern from essentially bidirectional to essentially unidirectional. And when you get that modest on-ground radial system to be used with a 1/8 wavelength, high inductively loaded vertical antenna, the best compromise to minimize near-field losses is a wire mesh screen at the antenna base. Beverage antenna, think of beverage as big. For best performance, it should be longer than one wavelength. Beverage antennas are huge. What strongly affects the shape of the far field low angle elevation pattern of a vertically polarized antenna? The conductivity of what's below it. Conductivity and dielectric constant of the soil. And one more time, that terminated rhombic antenna, unidirectional antenna terminated in a resistance equal to its characteristic impedance. Now remember that dish antenna, 20 dB, how many degrees? 20 dB, 20 degrees. 30 dB, it's going to be a much tighter pattern. 30 dB, how many degrees? 30 dB is, did you get it yet? I'm looking here. Wait a minute, I got it. 30 dB is 6.4 degrees. 20 is 20. 15 will be 36 degrees, and 12 will be a whopping 51 degrees beam width. So start off with 20 at 20, and you'll do just fine. Okay, it's reality check. You've made it all the way through all of the sub-elements in preparation for your upcoming license. On antennas, we had 5 exam questions out of 5 groups. Isotropic radiators was the first group. Then we had free space antenna patterns, and then all about phased vertical antennas, and then space and satellite communication antennas, and then finally matching antennas to feed lines, and transformation characteristics of line terminated in impedance not equal to characteristic impedance, and using antenna analyzers. Whew, boy. That's a lot of stuff. That is 50 questions out of a pool of 801 questions. And what we would like you to do now is to play over these audio courses, the different cassettes, part of the courses. And then when you think you're ready for the big review, on the flip side of this audio cassette, if you're listening to us on audio cassette, will be the big 45-minute review. Play that just before the exam. And on the review, we'll tell you exactly the number to call in preparation for the exam. So see you on the flip side.